Let us start this lecture with a thought process by Professor Propellant Roy, who was not only a freedom fighter, but considered to be the father of the chemistry in modern India. Of course, he worked before the independence, and he has written a book known as the Hindu chemistry. He also started a industry during British era on chemical technology. And he says a man may desire victory always, but he should welcome defeat at the hands of his own disciples. And this is a statement which he was quoting in the class when he was teaching in Presidency College, and he always referred this to from a sloka in our scriptures. So, this is a very profound statement to be a true teacher, and if some of you are interested to be a teacher, you should have this kind of mindset, so that the student can come up well. And let us recall what we learned in the last lecture. In the last lecture, we basically looked at various shapes of the liquid propellant rocket engines. We looked at only 3 of them. The most popular one at this moment is the cylindrical rocket engines, and also we discussed about the spherical rocket engine, which was used by the Germany during Second World War, and the in between, that is known as semi cylindrical or the spear rocket engines, which is a combination of spherical and cylindrical. And I also discuss about other various like your throatless rocket engines, and also the divergent rocket engines one can think of. And later on we looked at the various kinds of the propellant feed system, and that was broadly divided in 2 categories. One is your gas feed system or high pressure gas feed system, other is the turbo pump feed system. And we have analyzed that how to find out the amount of mass to be required for expelling the propellant in case of a gas feed pressure system. If you recall, we derived an expression by invoking the first law of thermodynamics, that is m naught, and that is the amount of gas required is equal to P p V p, and this is R u and molecular weight of the gas divided by T naught, and 1 minus gamma P r by P naught or initial pressure of the tank. If you look at, we have also looked at that the molecular weight of the gas will be decreasing, then the mass of the gas required for propelling or for pushing the propellant with a certain pressure can be reduced. And if the temperature will be T naught will be increasing, m naught will be decreasing. Beside this, if the P r will be a smaller one, right, and then this will be basically a bigger number and for a particular pressure. In other words, if P naught is higher as compared to P r, this will be a small quantity. If this is a small quantity, right, then naturally this will be bigger quantity, and then 1 minus that will give you basically smaller mass requirement for in case of a gas pressure feed system. And today we will be looking at turbo pump feed system, and we will see that how we can analyze, and for doing that let us take an example. Today we will be looking at turbo pump feed configurations, and there are various kinds of turbo pump feed configuration one can think of, but we will be discussing only 3 of them, and of course, this will be meant for bipropellant system, and for monopropellant system one can have similar in nature. So, let us consider a gas generator. This is one type of, if you remember, we have talked about gas generator type, and then we have also mentioned about the expander type of turbopump feed system and stage combustion turbopump feed system. So, let us look at this gas generator turbopump feed system, and in this case, as it is a turbo pump, the pump will be there to pressurize the fuel, and this is your fuel pump systems, and this is a centrifugal pump, and what is being used, so also the centrifugal turbine, and similarly the oxidizer line, oxidizer will be pumped through this oxidizer pump, and keep in mind this pump, centrifugal pump for oxidizer and fuel pump are connected to turbine, because to run this pump you need to supply the power from the turbine, and this is your shaft. And to start this pump you need to basically connect this thing to the high pressure chamber, right. So, therefore, that is very important one. If you look at, if I consider this as and this will be your propellant tank, this will be high pressure tank which will be connected, and also one can supply through this itself, and this is your oxidizer tank itself. That means, to start with it should have a high pressure tank as well, gas tank, high pressure gas tank. So, keep in mind that in this case, this is the initially this high pressure gas will be used to pressurize this fuel tank, and once this pump will started, then what will happen, the flow will be coming through that, and then it will be the some of the fuel will be diverted to this pre-burner, or known as the combustion chamber, right, or the gas generator. I can say rather better the gas generator. And similarly, oxidizer also when it will be diverted towards this, that, so that it will be burned, and once this burned gas, this high pressure temperature gas will be passing through the turbine and expanded fully, so that it will give the large amount of work, and this work through the gearbox, which is not shown, will be supplied to this both the fuel and oxidizer pump, so that it can run of its own. That is the beauty of this turbo pump feed system. It can run for a longer period of time, and as compared to the gas pressure system, this is more reliable and also can be modulated very easily. Rest of the propellant, which will be then going through this as a heat exchanger, and also the oxidizer can directly come and enter into this combustion chamber, such that it can be produce some thrust due to the expansion of combustion gas through the nozzle. This is your CD nozzle, right, CD nozzle. And keep in mind that this is basically one which is known as a gas generator kind of turbo pump system, and which is used for a very large engine, because that this expansion in the turbine is not dependent on the how it is combustion is taking place, because it is expanded fully to the low pressure. So, that the power requirement, power produced by the turbine will be quite high. and so that you can supply large amount of propellant and you can go for a high thrust rocket engines. And this is being used in the several configuration. One of them of course the F1 famous F1 rocket engine which is being used. Let us look at another case where there is no gas generator, and that is known as basically the expander. In this case the similar setup of high pressure feed system should be there just to initiate the flow through the pump and such that you can start the things. In this case the oxidizer pump which will be coming through that, and this is will be passing through a valve and can come directly to the combustion chamber, whereas the fuel pump will be passing through this nozzle, right, and then it will be taking the heat from the nozzle, even sometimes from the combustion chamber, so that it is basically vaporize itself or gasify itself, and then this gas can be expanded in a turbine, and then afterwards this again can be supplied to the combustion chamber, such that the combustion will be taking place between this fuel and oxidizer in the combustion chamber, and then it will be expanded in the nozzle to produce thrust. Keep in mind that in this case we do not have any gas generator. Here the liquid fuel which is generally can be used here, so that it will be gasified and then its pressure will be increased and such that it can be expanded in a gas turbine. Generally in liquid oxygen and liquid hydrogen system this kind of turbopump feed configuration is being used. And keep in mind that this is a very simple system, and the limitation of is that the pressure with which it will be expanded in the turbine must be greater than the combustion chamber pressure. That means the expansion should be as less as possible in the turbine, so that the work done which will be produced by the turbine will be much less, so that the pumping power of this pump will be low, or the pressure ratio across this pump will be much lower, and so also the flow rate. So therefore this will be used for a simpler system or a rather small systems, and it is also interdependent. That means the chamber cannot be operated at higher pressure to produce the higher thrust, because of the fact that it has to be expanded in a turbine, and that same fuel has to be now burnt in the combustion chamber. That is the reason it is used for a simpler and a smaller rocket engines with a low thrust and low ISP. So it is used in the R10 liquid oxygen, liquid hydrogen rocket engines. And let us now look at combination of these both. That is basically stage combustion, and in this case it is similar to that of the your gas generator. In this case the oxidizer is diverted, and however the fuel has to pass through the nozzle and sometimes the combustion chamber and then carry this heat such that this can be utilized for in the pre-burner, and when it will come in contact with the oxidizer, and this gas can be expanded in a turbine. Again this will be rich gas, right. That means very least amount of gas will be burnt, rest of the will be fuel pyrolyzed and gasified combustion products, or combustion or the fuel will be coming into this combustion chamber and it will be reacting, and then you will be producing the thrust. In this case the combustion takes place in stages. The first it is in the pre-burner or the gas generator, I can say GG, the gas generator, and then that has to be such that it will be burnt again in the combustion chamber, and this is having a higher efficiency as compared to the gas generator, because of fact that in this case in case of gas generator the heat is not really being utilized. In this case, heat being utilized in this case in the gas generator itself, and keep in mind that this is more sought after and it can be used for higher power rocket engine like space shuttle main engines. But among these three, the gas generator pre-burner is independent of the main combustion chamber. Therefore, this is the most preferred for the larger engine. Here there is a limitation, but however, the energy utilization good, and generally the expander is used for a smaller kind of rocket engines. So, there can be several permutation combination one can think of. However, we will be not discussing due to the paucity of time, and more combination permutation you can think of depending on your imagination to meet certain requirement. So, let us now look at how we can analyze the turbo pump feed systems and considering an example. A semi cryogenic engine consisting of liquid kerosene and liquid oxygen propellant rocket engine based on gas generator cycle feed cycle we have already discussed, is designed to produce ISP of 350 second and thrust of 750 kilonewton, and MR for the rocket engine is 2.5, and the temperature of the gas generator is restricted to 750 K, and the pressure change across the kerosene and the liquid oxygen pumps can be 4 and 5.5 megapascal respectively. The isentropic efficiencies of kerosene and liquid oxygen pumps are 0.85 and 0.9 respectively. The product gas from the gas generator is expanded in turbine with the pressure ratio of 15 and the isentropic efficiency of 0.9. If the specific heat and specific heat ratio of the combustion products from the gas generators happen to be 1.2 kilojoule per kg Kelvin and 1.2 respectively, determine the power of fuel and oxidizer pump and percentage of propellants to be supplied to the gas generator, and assume the mechanical efficiency for both fuel and oxidizer pumps to be 0.98. So, let us look at a gas generator pump feed system that we had discussed earlier, and we can learn how to analyze this pump feed system by solving this problem. Let us look at what are the parameters given, and this is your ISP is given as 350 second, and the thrust is 750 kilonewton. The mass ratio, of course, this is not exactly the mass ratio, but this is the oxidizer and fuel ratio. That is oxidizer, the fuel ratio is 2.5, and the density of the kerosene, that is fuel, is 950 kg per meter cube. The density of oxidizer is 1150 kg per meter cube, and the pressure change across, that is delta P of fuel is 4 megapascal and delta P of oxidizer is 5.5 megapascal, and the isentropic efficiency of the pump for oxidizer is 0.9, for fuel is 0.85. The pressure ratio across the turbine, you can say this is T I by T. T stands for turbine and exit is 15, and isentropic efficiency of turbine is 0.9, Cp of the gas I can say 1.2 kilojoule per kg Kelvin and gamma is 1.25 and mechanical efficiency is 0.98. So, we will have to find basically you will have to find out the power of the fuel, that is P of F and P of oxidizer. We will have to find out also the percentage of propellant, the percentage of propellants that is to be supplied by the gas generator. Like if you look at the amount of the propellant which is supplied to this gas generator, this is your gas generator, the this mg will be consist of mg of oxidizer plus mg of the fuel. And let us look at solution, and keep in mind that we are using isentropic efficiencies for fuel and oxidizer pump and so also for turbine, such that it can be really will be real situation. And if you look at this power to be supplied to the oxidizer pump will be equal to the P into delta V, right. That is P oxidizer or into delta P, whatever the change in oxidizer pressure into the volume, that is your volume of oxidizer, and that is in the ideal state, and then the real state it will be efficiency of oxidizer. This is the work done, and that is we can say that mass of oxidizer divided by density of oxidizer into delta P of oxidizer. So, mass flow rate of oxidizer we will have to find it out, right. And how we can find out the mass flow rate of oxidizer? That we can get because we know this ISP, we know this fuel. So, therefore, we can find out that. So, the total mass flow rate of the propellant, because we know that mass flow rate of propellant, this is your mass flow rate of propellant is equal to, that is F is your thrust divided by ISP and G naught is equal to, if you look at the is basically the 3 F is your 750 kilonewton and into 10 power to 3 divided by the ISP is 350 into the G naught is your 9.81, that happens to be something 218.4 kg per second. And we need to find out what will be the mass flow rate of the oxidizer and what is the mass flow rate of the fuel. And for that we will use this MR, and we know that M F is equal to m dot P divided by M R. So, similarly we can find out M of oxidizer is equal to basically M R divided by 1 plus M R M P. So, if I will take these values, right, M R is basically we know that M R is 2.5, right. M R is 2.5 divided by 1 plus 2.5, m dot p we have already found out, that is 8.4, that happens to be 156 kg per second. So, therefore, m dot f I can get m dot p minus m dot oxidizer, that is 218.4 minus 156 is equal to basically 62.4 kg per second. As I told earlier that power of the oxidizer is basically m dot oxidizer delta POX divided by oxidizer and rho of oxidizer. So, if I substitute those values, that is 156 into the 5.5 into 10 power 3 divided by 0.9 into the density 1150, I will get 829 kilowatt. This is a very big number. If you look at 829 kilowatt, around 0.829 megawatt. Similarly, we can find out the power of the fuel will be m of F delta P divided by fuel density of fuel. So, you will substitute this value, this is 62.4 into 4 into 10 power 3 divided by 0.85 into 950, I will get 309 kilowatt. So, now we need to find out what will be the percentage of the gas that we will be having. For that we will consider the turbine. So, if you look at this turbine, this is your inlet, this is I can say, and this is your exit, and in this case it will be, let us say PTI and PTE, similarly TTE and TTI. So, we can really find out that this is the work and it is connected to the pump. Keep in mind that this is connected to pump. Shaft connected to the pump on the both the side, both the oxidizer and fuel. So, if you look at, we will be balancing this the power that is of the turbine is equal to the pump. So, if you look at this thing, that we will get is eta T m dot T, this is the mass flow rate which is passing through m dot T, and m dot T remains same, and into Cp delta T, and is equal to the P dot A plus P dot oxidizer divided by the mechanical efficiency. This efficiency is basically mechanical efficiency. So, now if I look at this, I can write down m dot T Cp. If I take this TTI out, I can write down PT E by PTI gamma minus 1 gamma is equal to P A plus P oxidizer eta m. So, I am interested to find out basically m dot T, and then m dot T I can find out, this is P dot A plus P dot oxidizer divided by m into 1 over 1 minus P T E by P T I gamma minus 1 gamma into eta T and Cp T T I. So, if you look at this thing, all these are known. For example, P f, this is your basically 309 plus 0.829 divided by your 0.98 and 1 divided by 1 minus 1 over 15, because this pressure ratio is basically 15. And gamma already we know that is 1.25 minus 1, 1.25 into this is your 9.2 into 1.2 into 750. So, if you do that, you will get, substitute these values, you will get MT is 3.43 kg per second, and percentage of gas, that is nothing but your m dot g for generator is equal to m dot g divided by m dot f plus m dot oxidizer into 100. You will get 3.43 divided by 2, 8.4 into 100, you will be getting 1.57 percentage, which is a quite a low value if you look at, and that way generally the very small amount of the propellant is being used to run the gas generator, such that one can run the pump, and the turbo pump feed system can be really used. So, with this I will stop over, and thank you very much, and we will be discussing in the next lecture about the another topic, new topic. Thank you very much.